started in 2013, is led by Haystack MIT. And the project developed a beamformer that can aggregate the entire uncollecting area of the array. Basically, you align all the signals from individual antennas, and then you sum them up, okay? And then you get a much bigger signal. So you're turning all these antennas into a virtual giant single dish telescope. And normally we phase up, we say that, phase up, so aligning in phase these signals, about 41 antennas, and this corresponds to a single dish telescope with a diameter of 77 meters. And most of the other telescopes have 10, 12, 15 meters. Okay, so you can realize how much we gain with ALMA. That's why it's the anchor station for this kind of observations. All right, to conclude this part on the instrument and the observations, let me just add that we also coordinated a multi-wavelength campaign during the VLBI observations across the globe with the EHT, right? And these are summarized in these two plots. This is for SAGE-STAR, this is for MIT7. Here you have high-energy satellites, X-rays, you have NewStar, you have Chandra, but also we have some satellites in the TV and GV. We have Veritas, Magic, we have Fermi, and we have near-infrared coverage with the VLT. This should be somewhere. And some other networks that observe, a radio telescope that observe at lower frequencies. So we have a very good coverage of the electromagnetic spectrum, and this is very useful for interpreting the observations that we do with the EHT, okay? All right, so I explained quite a bit about all this data that we collect with the EHT, but you might ask, how do you get an image from all the signals that you collect at individual telescopes? Now, there are various aspects that go into this, and I'll try to quickly guide you through the main crucial steps, focusing on data processing and the imaging, which is the crucial step. So first of all, the EHT observations produce large amounts of data. In 2017, we recorded something like 4 petabytes. And this year, you know, we have a larger array, and we doubled the bandwidth. We recorded something like 15 petabytes. So it's a huge amount of data. We cannot transfer it over the internet. So what we do is we digitize the signal, we copy it in 10 terabyte disks, and then we fill literally big boxes, and we put it in containers and aircrafts, and we ship them, all right? We ship them to a center where the data is correlated. And in 2017, we filled something like half a ton of 10 terabyte disks. Some of them are shown in this room, but they are not even all of them, okay? So this is really big data science. Okay, so we ship all these hard drives to the correlation centers. We have 2. One is at Haystack MIT in Boston, and the other one is at the Max Planck Institute in Bonn. And you do this, a supercomputer that after synchronizing the signal does the correlation, okay? So you are recreating the interference pattern that I was telling you before, okay? And once you have the correlated data, we send it to the calibration teams, and then the calibration teams tend to remove all the distortions on the data that were applied by the instrument and by the atmospheric effects. And once the data are the best calibrated data that you can have, you send it to the imaging teams that use, specialized software to turn the calibrated data into brightness, millimeter waves. And so I can add something on the imaging because it's one of the most important aspects of the project. So this plot shows what we call the UV coverage. So you can imagine, so this is for MIT7, this is for SAGE-STAR. So you can imagine, just focus on one of these, that this is our virtual parabola, okay? And when you see colored dots is when you have measurements, okay? So if you like another analogy, these colored dots are, if this was a virtual camera, these are where you have pixels that are actually getting light from your source, right? And here is nothing, it's a broken camera, okay? So each pair of telescopes provides a pixel, okay, in this virtual camera. And you have only those that are active. But you don't see just a point for each pair of telescopes. These are pair of telescopes, right? You see these curved lines, right? These tracks. And this is because of Earth rotation. So this is shown better in this video. This video is showing the telescopes that are observing, the pairs of telescopes observing at each second, at each time. This is your virtual, the sampling of your virtual parabola, the UV coverage. And this is the image that you recover. And as you see how Earth rotation is crucial, because from a point you get these tracks, because as I said, Earth is rotated, so it's changing basically the orientation of your pairs with respect to the source. And the more Earth rotates, the more this gets filled up, and the more information you get on your source, and you can finally reconstruct. Initially, you don't know anything. You only know that there is some signal there, but you don't know what shape it has. And then as Earth rotates, you fill up the UV plane. So this means that we can get an image only after semi-rotation of the Earth, which means we have to observe for one night, an entire night. We can't have snapshot images with this technique, unfortunately, because it will be very important. But we have to wait for the whole night to synthesize our telescope. But the thing to point out is, even after one entire night, it's not that we have a very filled sampling, right? You have just a few tracks over there. What does it mean? It means that our sampling, our UV coverage is very sparse, okay? So somehow, if you want to get an image, you have to interpolate between these measurements in order to fill up your parabola. And now this is an issue, and is one of the difficult parts, how to interpolate to fill in the missing information. To reduce the bias in this process, we adopt a multi-stage procedure. As a first step, we created 4 independent algorithms. So they use different methods, different assumptions on how to fill this missing information. So we developed these 4 algorithms, but not only that, we also applied them in independent teams. So we randomly, we join our colleagues and we start working on the data without talking to each other, okay? It was mostly regional based, but I was with this team too, so there were people from MIT, so Americans as well, and Europeans and Japanese. So it's regional, but not geographically regional. And the reason to do this was to assess human bias. We wanted to avoid to have, shared human bias. Say, what are you getting? Yeah, maybe I should do this as well. Maybe I'm getting something wrong, etc., etc. And so we wanted to avoid shared human bias, but at the same time assess which were the common features that everybody will get, because those will be very robust, right? So, so we did that, and then as a third step, we built a large suite of synthetic data to exercise our imaging algorithms used by the different teams. So we considered 7 geometrical models that you see here. 3 are rings, okay, and other 4 are non-rings, but they are compatible with the data that we took, okay? And the way it works is this. You start from these theoretical models. You create fake data, so fake VLBI data that can correspond to these models. Then you take this data and you run them through your pipeline, your imaging pipeline, and you see the image that you get. And then you compare the image that you get with the ground truth, which is the starting point, and see if you get the same image or not. And this was a good exercise because it allows you to see the dependence of your images on your assumptions, okay? But not only that, it also allows to select fiducial parameters, top set parameters we call them, as input parameters in these imaging pipelines, okay? So we choose those set parameters, fiducial parameters, that would allow us to recover the ground truth images. So doing that, we obtained these 3 images. For M87, we had 3 algorithms. Initially, I showed 4. The 4th one was, we built it after for Sage Star. And as you can see, the 3 algorithms find more or less the same image, which was very reassuring. And we were very happy. Since we didn't want to be biased against one method, the image that we published was simply an average of the different methods. So this was all good for M87, but then when we went to do the same for Sage Star, The process resulted in thousands of images, all different in the brightness distribution in the ring. And since we could not choose one, because they were all compatible with the data, we wanted to have an approach that was as agnostic, objective as possible. So we took an average of these images, and this is the image that we published, okay? You might ask, what do we get one image for M87 and thousands of images for SAGE-STAR? These are two black holes, and the instrument is the same. They were observed on the same days, so there was nothing instrumental or anything like that. Well, this is because these are two different black holes. And the main issue is the variability of the black hole of SAGE-STAR. Why is it variable? I told you at the beginning, M87 is 1,500 times more massive than SAGE-STAR, which means SAGE-STAR is 1,500 times smaller. What does it mean? It means that a particle or a photon, it goes 1,500 times faster. How fast? Well, we can ask general relativity. We can, for example, use this formula that gives the dynamical time at the ISCO, the innermost stable circular orbit of a particle around the black hole, right? And this is a function of the mass. It's a linear function of the mass. And we get something like 30 minutes. Oh, this is Schwarzschild solution for people that know a little bit of general relativity. If your black hole is spinning fast, it can be even 10 times smaller, this dynamical time. So it goes from 4 minutes to 30 minutes. This is M87. This is our solar system. This is Voyager. So it's much bigger, and the time for a photon to cross the event horizon here is several weeks. What does it mean? It means that during one night, your source is static, M87. This other guy is continuously changing. It can change up to 100 times. And remember, an image is constructed with data acquired during one night. So you have a signal that is continuously changing, and you are trying to get an image of this, okay? So this is one of the main issues, and that's why SAGE-STAR is less symmetric and is a little bit fuzzier than M87. And one of the reasons is this variability, okay? We have a signal that is continuously changing. Not only that, there is worse. The other challenge, what is the other challenge? Scattering. Why? Because we are looking at SAGE-STAR, it's at the center of our galaxy, so we are looking through the disk, through all the ionized gas of the interstellar medium. What does the interstellar medium do? All the ionized clouds of the interstellar medium? Well, scattering has two components. One is diffractive scattering, where the effect is blurring, okay? So you have basically less resolution. But there is another component that is even worse, which is the refracting noise. Basically, has all the spurious components in your image. And this is stochastic, a time variable. So this is much worse. So basically, you get something that is more fuzzy and blurry. And that's why, like in this simulation, right? And that's why our final image of SAGE-STAR looks fuzzier than M87. And now I have the most technical slide of all to explain these effects. This is the complication of taking the image of SAGE-STAR with respect to M87. Okay, I said that we have this scattering effect. The scattering effect is like trying to take a picture of something on a rainy day from inside the house that is outside, looking through a very foggy mirror. And then the dynamics of the system is represented by a dog chasing its tail. So this is SAGE-STAR. That's what we are trying to do. Try to take a picture of this. That's what you get, right? You can't even see that it's a dog. You can see that it's a dog that is kind of chasing its tail, but I had to tell you probably. And this is M87. It's very easy to take a picture of this dog in the living room, right? So this explains why to get the picture of SAGE-STAR took us 3 years longer than M87. People said, well, you did the first time, so you must have understood very well the data, you have all the algorithms. No, because we had to build new algorithms to deal with this, the dynamics and the scattering. And that was 3 years more of our lives trying to get the image that you saw, okay? So I think I've spoken already quite a bit, but you must have realized by now that EHT is a project based on acquisition and process of large amounts of data that's complicated, right? So I wanted you to take that point home, because people see a fuzzy image and say, okay, whatever, right? So why are they making such a big fuss and why are they taking so long? But I guess many of you are more interested in the implications and what this means. So I can try to squeeze a few information if I can have 5 minutes, maybe longer than this, but maybe it's a bit more interesting for you that are not really astronomers and not that interested in data analysis from interferometric data. Okay, so I'll try to be quick here. So what changes now is that black holes are not abstract concepts anymore. They are not just a solution to an equation or a theory. We can use them as laboratories to study processes, accretion process, for example, in black holes, the formation of relativistic jets, but most importantly, we can use telescopes to basically understand black hole physics and gravity, okay? And in our collaboration, we do extensive modeling to interpret our observations. The core of theoretical work, as I was introducing before, is provided by numerical simulations, and this numerical simulation use this general relativistic magneto-hydrodynamic codes, okay? We basically provide the physical conditions of the plasma orbiting the black hole, and here you need to fix the black hole space-time, so the theory of gravity. This can be GR, but can be also an alternative theory of GR. It depends on the parameters of the black hole, the spin, for example, but also some physical parameters of the plasma. For example, the state of accretion. Some of you might have heard of these models, sane models and mad models. So these are strongly magnetized accretion flows. And a third ingredient, as a third ingredient, we use radiative transfer modeling. We have this ray tracing codes, also in general relativity. So this is general relativistic ray tracing or radiative transfer codes, and also in this case we need an input, the black hole mass, for example, the accretion rate, and we also include some microphysics. And as a final step, we need to link theoretical models to observations. So we basically create synthetic images, assuming observing parameters which are the same of our instrument, and then we use these images created with the ray tracing codes, okay? And we create synthetic images. So we use this as input, and we simulate that we are observing them with the same instrument that we have, and we get this, okay? These are synthetic images. And then we compare these synthetic images with what we observed, right? So we did this for MT7. We had over 60,000 different simulated images, and each image uses different parameters. We change slightly the masses, the inclination, magnetic field prescription, the electrode temperature, the plasma temperature, and so forth, okay? And that's why they appear all different. Some are more asymmetric, some have more structure, but they all have one thing in common, okay? They are ring-like, and they have the same size of the ring. So we see this dark patch at the center of rings, which is the signature of the black hole shadow, okay? And that's the important part, the GR signature that we are after. For Sagittarius star, we created an even larger library. We created 2 million images, because this was necessary to account also for these other complications like time variability. And we produced 2 million images at different frequencies, so different wavelengths, if you will, 1 millimeter, 3 millimeter, and also 2.2 micron. And we compared these 2 million images with 11 different observables. 6 are coming from the EHT, but then I told you that we had the multi-wavelength coverage, so we also compared to we use measurements from a telescope observing at 3 millimeter and also in the near infrared at 2.2 micron, okay? And what we found was that the best bet models are strongly magnetized, the ones that we call the MAD, and they have a positive spin, high spin, so no zero, no Schwarzschild. And then the accretion rates are between 10 to the minus 8 and 10 to the minus 9 solar masses per year, okay? Now, besides these accretion models, black hole accretion models, perhaps the most important application is to use this opportunity of these images to do tests of GR, right? So the most relevant question is if these two images are consistent with general relativity. And qualitatively, just based on the image morphology, yeah, we can already say that this bright ring around the dark patch at the center is consistent with the emission from the photon ring, right, around the black hole and the shadow, okay, as I introduced at the beginning and as we see in all these simulations, right? But of course, we can be more quantitative and extract parameters from our measurements, and we compare to theoretical predictions. And from the image, we can get the size, the shape, and the asymmetry, at least in M87. In GR, we know that the size is proportional to the mass, okay? Well, the mass divided the distance because it's an angular size, but you get that. But it can be 7.5% smaller if the black hole is spinning. For a maximally spinning black hole, it can be 7.5% smaller, okay, than the Schwarzschild solution. And then the shape is a perfect circle for a Schwarzschild solution. So for a black hole that is not spinning. And then you have a few percent departure from circularity if you have a spinning black hole, but also if GR is not correct. Okay? Unfortunately, the two effects are coupled. So if you want to constrain, if you want to use these images and see deviations from GR, you gotta know the spin. Because otherwise, one effect could be due to the spin and not to a different space-time. And finally, the asymmetry. Okay, in M87, this asymmetry that you see here, we interpret it as, with this GR effect, which is Doppler beaming or Doppler boosting. What you have is that the radiation that is coming towards you is boosted, and the one that is coming away is dimmer. And this is what you see here. So this stuff is coming towards you, and this one is going away, okay? And from this, we knew that the plasma is going clockwise from this. Here we cannot say that because we have these three spots which are actually spurious, and if you are curious, I can show you some more slides on this, but I took it out from the presentation to be shorter, okay? And then we can compute the size and the shape. For example, we can fit the peak of the brightness distribution in the ring, and it turns out that we cannot measure circularity to better than 10%. And if you remember, I told you that the spin can change by 7.5%, so we basically cannot tell, we cannot estimate the spin from these images because we don't have enough accuracy in our images, but we can focus on the mass, okay? And in M87, we had two previous measurements of the mass. One comes from gas dynamics. This is Lyman alpha hydrogen line, the one to the left. So this is gas that is in a disk that is about, it's not written here, but I think it's 20 or 40 parsec. Across, okay? And then you have stellar velocity dispersions in a disk that is similar, 60 light years, so that means that this should be like 20 parsec, okay? And as you see, there is a factor of 2 difference, a discrepancy. So both of them use Kepler's law, yeah, to get the mass, so nothing fancy like general relativity or Einstein, okay? So there is a factor of 2 discrepancy. We can use general relativity, Schwarzschild radius. This is the formula I used before. There was a measurement of the distance, about 70 megaparsec independent. If you have the distance, if you have the distance, then you can get a mass. And then you get a mass of 6.5 billions solar masses, right? And this is very much in agreement with the stellar velocity dispersion measurements, okay? Now, to understand the depth and the beauty of this consistency, consider that a photon to cross the event horizon in M87, so we are looking at regions that are, tens of light hours. A photon takes 40 light hours in this graph to cross the event horizon. This is what we are probing with our image. Here we are talking about 60 light years, okay? And we get the same mass. That means that's a beautiful result because the theory of gravity should be valid and the same both in the weak field regime far from the black hole and a strong field regime very close to the event horizon. So this is a very good test of GR. The mass is the same in the strong field and the weak field regime. We get the same, the measurements are consistent. Now, for Sagittarius, I'm sure many of you are familiar with this. We had a much better measurements of distance and mass thanks to this monitoring of the stellar orbits at the galactic center that were made with VLT and the Keck interferometer, and the Keck telescope using adaptive optics. So this experiment followed the orbits of about 30 stars within 10 arc seconds from Sagittarius. Just using Kepler's law, you will get that they were all moving around a dark spot that must have had 4 million solar masses, okay, to explain velocities up to thousands of kilometers per second of these stars, and especially the stars within 1 arc second, the S stars, right, that allow our colleagues to get a Nobel Prize in 2020 for these measurements. These S stars, specifically the S2 star, provided the most precise estimate of Sagittarius mass and distance so far. I didn't include the Nobel Prize picture this time. So these are the last values that we have, the mass, the distance from the two groups, Keck and VLTI. We can get their ratio, so we can get the angular size of the Schwarzschild radius. And it's something around 5 microarc second, right? And so there is a discrepancy, but a difference of something like 7%, which is due to the fact that the two groups found a difference in mass and distance of about the same amount. But for us, it's not important in the sense that we took both of them and calculated and did the test using both priors. So that describes a little bit our GR test that we did. So we use mass and distance from the optical telescopes to calculate this gravitational radius angle, whatever. It's an angle, okay? Then we use this to get the shadow diameter, which is this simple formula that comes from GR, okay? Then we measure the diameter in our shadow, in our images, and we compare it with this theoretical value. This is Schwarzschild, and we add these delta parameters to account for deviation. For example, if we compare what we measure with the theoretical prediction, if delta is 0, that means perfect match. So what we are seeing is exactly Schwarzschild black hole, okay? If this delta is different, there is a deviation. But what does it mean, a deviation? Well, Schwarzschild is a black hole that is not spinning. If it's spinning, I told you that the size can be 7.5% smaller, which means if delta is between minus 0.075 and 0, this is called Kerr, right? If you have a spinning black hole, the solution of the black hole in general relativity is called Kerr, from the guy that came out with this solution, like Schwarzschild, right? So if we are in this regime, then our shadow is consistent with general relativity, spinning or not spinning. And these are our results. So forget about the table. So these curves here are showing you this delta parameter from this comparison here, and for this comparison here. And there are many curves because we are comparing different imaging algorithms and also different ways to measure the shadow from the image. Okay, there are details that I want to skip. What is important is this purple shaded area here, which is indicating the Kerr solution. 0 here means Schwarzschild. Okay, the black hole is not spinning. If it's spinning, it goes a little bit smaller. So the more you move to the left, to the left, the more spinning the black hole is. And as you see, our curves are well this shadowed area, right? So our conclusion is that what we get is consistent with prediction of GRs, in particular for a rotating black hole, which we call a Kerr black hole, within 10%. Okay, this is our accuracy. Again, it's within 10% our accuracy, so I can't tell how spinning the black hole is, right? So unfortunately, we can say that, but at least we can say that it's consistent with GR. Obviously, we would like to make this statement with 1% accuracy and not 10%. If we had 1% accuracy, then we could probably get a spin, and maybe we could do test of GR and test alternatives to GR. We are not there yet. This is actually part of the future, because What I showed you before were images obtained with the first year campaign, okay? We got other 3 campaigns, and there is one this month. This year I'm not observing. And so we have like 4 different campaigns of data to analyze. We are adding telescopes, which means that the fidelity of our image will be better because you have a better sampling on the UV coverage. So the images that we will get will be more accurate and more higher fidelity. More important, we are pushing to shorter wavelength, higher frequencies. So we will be observing this year 345 gigahertz with respect to 230 gigahertz. So we are going to improve our resolution by factor by 50%, okay? And one day we dream about putting satellite in space. Then you can increase the size of your telescope with, obviously, satellites that can be, there are no limits anymore but the size of the Earth. Okay, I think I spoke almost an hour, I'm sorry. But I'll thank you all for sticking till the end, and I'll take questions if you have any. Thank you.
Thanks, Ciriaco. Excellent talk. It was good to get your computer running to show all the videos.
Yeah, I knew that, right? So it wouldn't be the same with me trying to, mimicking all the movies. I move already too much as in Italian, so you can imagine. Luckily, you gave me this, so there is some constraints.
So, do we have questions? Okay, Simone.
So thank you very much for guiding us through this technological challenge
Exactly.
adventure. And my question is, you mentioned that about placing telescopes in space. So with this architecture, do you think it would be possible to observe, for example, stellar black holes?
No, they will be always too small. So stellar mass black holes cannot be resolved, no matter how far you put the satellites. But I forgot this. But our hope is that we will be able to observe an important sample of black holes, maybe 10 to 20, no thousands, even with geostationary satellites. But even adding 10 different black holes with different masses, it will be very beneficial to understand black hole physics. Now we have some kind of gap between 4 million solar mass black holes. It just started 6.5 billion solar mass black hole. M87 is one of the biggest black holes in the universe. So we need to sample the range, but stellar mass black holes, we will have to use gravitational wave detectors, and there will be a bright future with the Einstein telescope. Is something that I'm really keen on. One of the sites to build the Einstein telescope, I don't know if you guys heard it about this future gravitational wave detectors. Is Italy, and is the island of Sardinia where I'm from, and it's actually very close to the village where I grew up. So it's kind of exciting thinking that it will be one big experiment on black holes and gravity and the origin of the universe, because the Einstein telescope will be also working on cosmology, that it will be so close to home, but not with EHD. But that's why we are starting to, some kind of collaborations with the gravitational wave community, because there are synergies. There are things that they can do, and we can do the stellar black holes, right? So unfortunately. We do have one of our targets. It's called OJ287, and is one of the best candidates that we have as a binary supermassive black hole. It's a billion solar masses binary black hole, and it's one of our targets. And obviously, we don't have the same resolution, so it will be mostly to look at the smaller scales of the jet that's coming from this binary black hole. I don't know if we will be able ever to resolve the binary. Actually, I didn't check the numbers for this. I don't think so for this one, because it's pretty far. But luckily, there is some candidate that we can get close to resolve the binary black. That would be amazing. Yes. So we have some candidates. These are all candidates, by the way. These binary supermassive black holes. There are models that fit the data, but obviously we don't know for sure that it's a binary black hole. But we have a few in our sample, because I show you two supermassive black holes because we get the images of their shadows, but we normally observe during 1 week of LBI campaigns is something like between 10 and 20 AGN. Okay, and we have also binary black holes. Yeah.
So that would be my second question, was about stellar mass black holes. Sorry. So, what kind of evidence we can expect to not observations, but what kind of evidence we can expect from stellar mass black holes?
So there are two issues. One is resolution, okay, and forget about it. And then the other thing is that this regime of radiation is not good to observe stellar mass black holes. So you better observe them in high energy telescope, in X-rays, because you don't have this strong emission at millimeter waves. I don't even know if there is any detection of stellar mass black holes at this high radio frequency. So it's not a very efficient regime to observe these objects, but it is very efficient for us because we have these REF processes, and we get the some millimeter bump. And for stellar mass black holes, the peak is not in the radio, it's somewhere in the X-rays. I'm not an expert, okay, so I'm a radio astronomer, but I understand that the peak of the emission cannot be in the radio, so it just doesn't make sense to use this complicated system to observe stellar mass black holes. Here.
About the data reduction process to obtain the black hole image, how long does the whole process?
So, so I say that it's a lot of data, but in the end, it's not the computing time. Maybe at the first step, the correlation takes longer because we call it data reduction, right? For a reason, because first it's big and then it gets smaller and smaller, right? You integrate in time and you correlate the signals. But it's a matter of days of processing and also to run the pipelines. In the end, it's a matter of days. What takes time is the manual inspection of the time, understanding the data. So in total, it took us 2 years from data acquisition to publishing the images because we were understanding the data. So yes, we need some cluster with a lot of cores to process all this data, but it's not like the bottleneck. It's not that with 10 times or 100 times computing resources we will be faster. We'll need 10 times, 100 times more postdocs. Skilled postdocs to be looking at the data. That's more efficient because you need to understand. I didn't go into details, there was no time, but imagine this is an interferometer that is across the globe, but it's not only that, and they are all observing independently and not in real time. They are all different. One is big, one is small, one is on top of Mauna Kea, one is in Sierra Nevada, you know, where people go to ski. Conditions are very different. The size of the dishes are very different. Viewing times are very different. And then you're looking at this data, and each telescope has its own thing. And you have to understand every telescope, every couple, in that moment, what the hell is going on here? So that's where all the time goes. So there will be always needed human intervention. I was so lucky to have a very smart student that developed a pipeline, which is semi-automated pipeline to process this data, and a lot of things can be done automatically. But even the smart student could now, make a machinery that works pressing a button. Okay, this works for interferometers like ALMA, You know, the observatory has invested a lot of money. It's a €1 billion observatory. You have people that are paid to develop pipelines. The antennas are all the same. And they built pipelines. It took years to build pipelines, you know, that can run. And also, the analysts do the work for you. And then the PI gets basically the raw data with the calibration tables to be applied in a script. So they have already the calibration, and the script just reads the tables, and then you get the final image. The only thing that is missing is the paper, right? But that is for the PI to write. But in this case, it's not going to be possible. VLBI is just too complicated. Yeah. But if you are interested, I would be happy, you know, to get some novices here.
So just before I hand over to Julia, who has a question or comment, that it said that we need 100 postdocs, but these days it's all about AI, right?
Yeah.
Just deliver to ChatGPT and we'll do all the work, right? You just need AI. And curiously, today there is a release from the EHT, right? Using machine learning that they reprocess the donut, producing a thinner donut. So related to that about ALMA and being, I mean, it's the most important part of the array and have more streamlined pipelines at all. ALMA by itself could come any closer to any of these images. What's the limit for ALMA? What can ALMA do by itself?
So I work mostly in this project on the ALMA data, and maybe I have some nice pictures. So that was a nice picture that we made for the ISO messenger, but I think there is a better one. This, by the way, is Centaurus A, for people that work on radio galaxies, extragalactic jets. I don't know, it's a very nice result that a former student of mine got. There must be something on, yeah, maybe this one is not the best, but so the problem with ALMA is an interferometer, but as I said, the separation between telescopes is what gives you the angular resolution, right? So you have a plateau in ALMA, and the longest separation between telescopes is 16 kilometers, while we have 10,000 kilometers. So ALMA has a resolution that can be at best tens of milli arcseconds, and we have tens of micro arcseconds. So we have 1,000 times better resolution, and thus, God damn it, what happened here? So this is a nice result that we obtained with combining EHT and ALMA on magnetic fields. So with ALMA, you can see the full jet of 97. So it has this jet that is across several light years, okay? And with the EHT, you see the core of the jet. So if you combine the two, in this case, this is a paper that we published in 2021, you can basically have a description of the magnetic field from horizon scales along the relativistic jet, okay? So the combination of ALMA and EHT allows you to sample very different scales, but this is very important to understand basically the origin of the launching mechanism of relativistic jets, which is an open question for 50 years, right? What is launching these relativistic jets? A magnetic field is obviously one of the main ingredients that we need. So I didn't have time to talk about magnetic fields, but ALMA helps a lot in this because of the sensitivity and the purity of the instrument. So I work on polarization for many years on this, yeah. Oh, that's the beautiful jet. These strikes that you see here, these are polarization vectors, okay? So the magnetic field should be perpendicular to this. Look at this. For thousands of light years, you have an ordered structure. Then something happens here. There is a shock region here. There's a knot, and this is beautiful. It's a beautiful result. Somebody else had a question.
Hi, hello. Thanks for this very interesting presentation.
Thank you.
I have only one question, and it's probably very simple. When you combine the different different frequencies, how do you avoid 2π uncertainties in this combination?
By different frequencies, you mean
Data from different telescopes, for instance. How do you, instead of staying like this, how do you avoid, for instance, combining the fringes like this?
Well, we take care of that with our software. So this whole process that is done at the correlation. So back in the day was with magnetic tapes, so you had to do this process multiple times. Now you have this, they're called fringe searches windows, and then you basically overlap the signals there at the correlation. You take care of this phase wrap up, basically. So that's not a huge issue. It's something that we can solve with the software. Yes.
Do we have more questions? Come on, don't be shy. I know you want to know all about binary black holes. So yeah, about binary black holes then, since it was raised. I mean, it's sort of uncommon, right? I mean, at least we think that there isn't a list of supermassive binary black holes around to get. And about your next targets, Andromeda will be there. What's next? Give us some spoiler.
Yeah, I know. One thing about Andromeda, because it's nearby, but in the end it's not that different from Star. Obviously, Star we wouldn't see it if we were a little bit farther. So it's too far, unfortunately, and it's not even a strong emitter at radio waves. So it's a bit like having Star, but the location of Andromeda. So unfortunately, it's not one of the target. I think somebody looked at this, and both the brightness and the size are low. So I don't think we will be able to do it. But you know, with the satellites, the problem is that you get this higher resolution, but then you are less sensitive. Because you have to think, if you have a bigger telescope, then basically you are spreading the brightness, you know, in a smaller pixel. So your telescope has to be, your signal has to be stronger, otherwise you won't see anything. So the higher your resolution, the less sensitive you are, and that's a problem. And with satellites also, we cannot make it that big. So now we are, it's not a design phase, we are proposing, like part of a group that is proposing, what is it called? A proof of concept. No, it has a different name, TWISA. And we are looking at 6 meters radio telescopes, which is still too expensive to build and is still too small. We need at least 10 meters. We will need at least 3 satellites, and that's very expensive. And then the other problem is 10 meters to get enough collecting area. What do we do with the data? We can transfer petabytes of data from the satellites. Do we do the computing there? Okay, then you have to transfer the data and do the computing there. And then instead of transferring petabytes, you transfer terabytes. Maybe that's possible. So we are in that kind of phase. So sensitivity is going to be a problem if you want a bigger telescope, because then the two things go in opposite directions, right? And the satellites cannot be bigger than the telescopes we have here.
And you want to measure on higher frequencies, right? So it's super millimeter.
Yeah, so but we cannot go to higher frequencies. So now we are going to do 345 gigahertz. But then there is a limit. For example, there are not many telescopes on Earth that can observe at 600 gigahertz. ALMA can. YAMA, the Argentinian, Brazilian telescope, will be able to, because it's in the Andes and it's very dry. Mauna Kea, Hawaii, can. But then Sierra Nevada can't. Alps, we have Plateau de Bure. in the Alps can't. Arizona most likely can't. South Pole, I don't know, but we have Greenland, but you know, these are difficult. So maybe we have 4 or 5 sites for now that can observe at, you know, something that is a sub-millimeter, so smaller than 1 millimeter. But it's much, much harder. Because yes, increasing in frequency will allow you, obviously, to have a greater resolving power. But we are at the limit. Yeah.
I mean, for the satellites, it's also harder, right? Because you need
yeah, the satellites.
More care in the design.
Well, the satellites, there is you don't have the problem of the atmosphere, so you can observe a very high frequency. You can observe 1 terahertz, no problem. The problem there is the size of the dish and how to get the data. But that's a technological problem, and maybe in 20 years or 30, we are. What was the design? We call it 2050. Something, this is a call for proposals from ESA. So it's 30 years from now. So maybe the data transfer problem will be solved. But the dish size, I don't know. Well, maybe you can send these dishes that then they are assembled in space, you know? And maybe that's possible one day. I don't know. Yeah.
No more questions? Okay, so let's thank Ciriaco again.
Thank you.
Excellent.